Good day, everyone. Today we'll be discussing series. What do we mean when we express a number as an infinite decimal? For instance, what does it mean to write? But there are other situations in which we implicitly use infinite sums. For instance, in decimal notation, the value of pi is 3.1415926535 and so on. The convention behind our decimal notation is that any number can be written as an infinite sum. So pi is equal to 3 plus zero point 0.1 plus zero point 0.04 plus zero point 0.001 plus zero point 0.005 and so on. We can literally add infinite number of terms, but the more terms we add, the closer we get to the actual value of pi. Let us now consider this to be an infinite sequence or infinite series. If we try to add the terms of an infinite sequence, so the sum of an infinite sequence is a series. For the infinite sequence a sub n for n equal to 1 to infinity, we get an expression of the form a sub 1 plus a sub 2 plus a sub 3 up to its limiting value L plus a sub n to L, which is called an infinite series, or we call it just a series. And this is denoted by summation of a sub n for n equal to 1 to infinity. So by default, the starting point would be n equal to 1 to infinity. So we may write any different value for the starting point when we choose to start at different point except for n equal to 1. And if it is not an infinite series, so we can have it as a finite series n equal to b. It would be impossible to find a finite sum for the series 1, 2, 3, 4, 5, and so on up to n. Because if we're going to add this term, then we get a cumulative sum that grows increasingly larger. However, consider this series of distances from Zeno's paradox: 1 half, 1 plus 1/4, plus 1 over 8, plus 1 over 16, plus 1 over 32, plus 1 over 64, up to 1 over 2 raised to n. So if we start adding this term and we keep track of the subtotals as we go, we get, initially, we have the first sum to be 1 half. So for n equal to 1, we have 1 half. For n equal to 2, it would be 1 half plus 1/4. So that would be 3/4. When n is equal to 3, so we have 1 half plus 1/4 plus 1 over 8. So that would be 8 over 8 times 1 half plus 1/4 plus 1 over 8. So that would be equivalent to 1 over 8. 8 over 2 is 4. 8 over 4 is 2. And 8 over 8 equal to 1. So 4 plus 2 plus 1. So that would be 7 over 8. And then when n equal to 4, so it would be 1 half plus 1 fourth plus 1 over 8 plus 1 over 16. So this is 7 over 8 plus 1 over 16. So we can have 16 over 16 times 7 over 8 plus 1 over 16. So we have 1 over 16 times 16 times 7 is 16 divided by 8 is 2 times 7 is 14 plus 16 over 16 is 1 times 1 is 1. So we have 15 over 16. So as n increases, the next sum would be 31 over 32. And then after that, we have 63 over 64. And so on. For the table of sums, so the table shows that as we add more and more terms, these partial sums becomes closer and closer to 1. So as n becomes 25, it would be 0.99999997, so approximately equal to 1. In fact, you can verify that the nth partial sum is given by 2 raised to n minus 1 over 2 raised to n, which is equal to 1 minus 1 over 2 raised to n. And we can see that by adding sufficiently many terms of the series, making n sufficiently large, the partial sums can be made as close to 1 as we like. So it seems reasonable to say that the sum of this infinite series is 1, and we write the summation of 1 over 2 raised to n for n equal to 1 to infinity would be equal to 1 half plus 1 fourth plus 1 over 8 plus 1 over 16 plus L plus 1 over 2 raised to n plus L equal to 1. We use similar idea to determine whether or not the general series summation of a sub n has a sum. By the way, this is the sum of a geometric series. The sum of a geometric series is a times for an infinite geometric series, the sum is a sub 0 over 1 minus r the first term being 1 half. So the first term is 1 half. And the common ratio is also 1 half. So we have 1 half over 1 minus 1 half. So that is 1 half over 1 half equal to 1. For the sum of, so if we are going to consider that this is not a geometric series or an infinite series, we can use the partial sum. So if we have a geometric series, a plus ar plus ar squared and so on until ar raised to n minus 1, the sum is sub n is equal to a times 1 minus r raised to n over 1 minus r. So you can see that the first term is 1/2, and we will be having 1 minus 1/2 raised to n over 1 minus 1/2. So we can say that the sum is 1/2 times 1 minus 1/2 raised to n all over 1/2. So this is 1 minus 1/2 raised to n. So 1/2 raised to n would approach 0 as n becomes large. So it would be 1. Now take note that this formula 2 raised to n minus 1 over 2 raised to n comes from this one. It would be 2 raised to n minus 1 over 2 raised to n, 2 raised to 2 minus 1 over 2 squared, 2 cubed minus 1 over 2 cubed, 2 to the fourth minus 1 over 2 to the fourth. So, but basically, we can use a certain formula to evaluate that. So, if we will be considering the partial sums, the first sum is 1/2, your a sub 1. Your second sum is a sub 1 plus a sub 2. Your third sum is a sub 1 plus a sub 2 plus a sub 3, and so on. In general, the sum S sub n is equal to a sub 1 plus a sub 2 plus a sub 3, and so on. These partial sums form a new sequence S sub n, which may or may not have a limit. If the limit S sub n exists, as in the example, then we can call it the sum of the series, or the sum of the infinite series summation of a sub n. Given a series summation of a sub n for n equal to 1 to infinity, wherein it would be equal to a sub 1 plus a sub 2 plus a sub 3, let S sub n denote its nth partial sum. So S sub n is equal to the summation of a sub I equal to a sub 1 plus a sub 2 plus L up to a sub n. If the sequence S sub n is convergent and the limit S sub n as n approach infinity exists as a real number, then the series summation of a sub n is called convergent, and we write a sub 1 plus a sub 2 up to a sub n equal to S, or the summation of a sub n equal to S. The number S is called the sum of the series, and the sequence S sub n is divergent. So if the sequence S sub n is divergent, then the series is called divergent. Thus, the sum of a series is the limit of the sequence of partial sums. So when we write the summation of a sub n equal to S, we mean that by adding sufficiently many terms of the series, we can get as close as we like to the number S. Notice that the summation of a sub n for n equal to 1 to infinity, so if we're going to have the sum of the series, it would be the limit of the summation of a sub I for I equal to 1 to n. Suppose that the sum of the first n terms of the series summation of a sub n for n equal to 1 to infinity is equal to, so let us have the general term for the sum of the series. The general term for the sum of the series is given by 2n over 3n plus 5. So the sum of the series is the limit of the sequence. So what we're just going to do is to evaluate the limit of the sequence as n approach infinity. So we can divide both numerator and denominator by n. That would give us 2 over 3 plus 5 over n. And as n becomes bigger and bigger, so that would make your 5 over n approaching 0. So that would be 2 over 3. Or we can apply L'Hopital's rule. So that would be the limit of 2n over 3n plus 5 as n approach infinity. So this would be an infinity over infinity. So evaluating the limit, so it would be 2 over 3. So taking the derivative of the numerator, so the derivative of 2n is 2. The derivative of 3n plus 5 is 3. So as n approach infinity, so it would just be 2/3. So there is a value that we have computed for the sum of the series. So this series is now convergent. Now let us compute for the sum of some known series or some sequences. An important example of an infinite series is the geometric series. The geometric series is given by A plus AR plus AR squared plus AR cubed and so on and so forth up to AR raised to n minus 1. This has the general form AR raised to n minus 1 where the starting point should never be 0. Each term is obtained from the preceding one by multiplying it by the common ratio r. If r is equal to 1, so it would just be 1 plus 1, a plus a plus a plus a. So that would be na as n approach infinity. So it would be infinity. Since the limit s does not exist, the geometric series diverges in this case. So if a is positive, it would be positive infinity. If a is a negative number, so it would be negative infinity. So since the limit s does not exist, the geometric series diverges in this case. If r is not equal to 1, so we can derive the formula for the sum. So s sub n is equal to a plus ar squared and so on and so forth until ar raised to n minus 1. If we multiply this by r, so we will be having r times the sum is equal to ar plus ar squared plus and so on and so forth until ar raised to n minus 1 plus ar raised to n minus 1. The next thing to do is to subtract these two sums. So we will be having s sub n minus r s sub n is equal to, so these terms are common. So the difference is a minus ar raised to n. So the sum s sub n is equal to a times 1 minus r raised to n all over 1 minus r. So take note that this becomes 1 minus r times s sub n is equal to a times 1 minus r raised to n. So that would give us the formula for s sub n equal to a times 1 minus r raised to n over 1 minus r. So, we're going to evaluate this as n approach infinity if we have r in between negative 1 to 1. We know that r raised to n would approach 0 as n approach 0. So if you have a fractional component less than 1, raising it to infinity or raising it to a very large number, it would approach 0. So this term would approach 0 as n approach infinity. So the new formula would now be a times 1 over 1 minus r minus a times r raised to n over 1 minus r. Taking note that this would approach 0. So we will be having the sum to be a over 1 minus r. So thus, when the absolute value of r is less than 1, the geometric series is convergent and its sum becomes a over 1 minus r. If r is less than or equal to negative 1 or r greater than 1, the sequence r raised to n is divergent, and so equation 3 s sub n does not exist. So, on our interval from negative 1 to positive 1, if your r is greater than 1, divergent series diverges. When r is less than negative 1, the series also diverges. So take note that when it is less than or equal to negative 1, it diverges. And when it is greater than 1, I think greater than or equal to 1. So when it is equal to 1, it also diverges. And it only converges from negative 1 to positive 1. So it converges when r is in between negative 1 and positive 1 exclusive, not including negative 1 and 1, and it would diverge if it is less than or equal to negative 1 or greater than or equal to 1. So just to summarize that for geometric series, we summarize this result as follows. The geometric series, summation of ar raised to n minus 1 for n equal to 1 to infinity, equal to a plus ar squared and so on, is convergent when the absolute value of r is less than 1 and its sum ar raised to n minus 1 of equal to a over 1 minus r, where r is less than, where r is the absolute value of r less than 1. And if the absolute value of r is greater than or equal to 1, the geometric series is divergent. So there is no sum if r is greater than 1, greater than or equal to 1. Now let us have the test for divergence. How do we determine if the test is divergent? Find the sum of the geometric series 5 minus 10 over 3 plus 20 over 9 minus 40 over 27 and so on. So, applying the concept for geometric series, so you have a sub 1 equal to 5, a sub 2 is negative 10 over 3, a sub 3 is 20 over 9, a sub 4 is negative 40 over 27. We're going to test whether this is a geometric series by taking the common ratios. So, common ratio is negative 10 over 3 over 5 equal to negative 2 over 3. Another common ratio, 20 over 9 divided by negative 10 over 3. 20 over negative 10, negative 2 over 3. Common ratio, negative 40 over 27 over 20 over 9. Also negative 2 over 3. Since the ratio is is in between negative 1 and positive 1, so we can say that this is convergent. So for a convergent series, the sum is equal to a sub o or a sub 1 over 1 minus r. The first term is 5 and the common ratio is negative 2/3. So 1 minus negative 2/3. So the sum would be 5 over 1 plus 2/3. We multiply both numerator and denominator by 3. So we have 15 over 3 plus 2. So the sum is 15 over 5 equal to 3. So we have proven that it is convergent with the sum equal to 3. We know that the series is divergent if its sequence of partial sums is a divergent sequence. So again, we know that a series is divergent if its sequence of partial sum is a divergent sequence. Show that the sum or show that the harmonic series is the reciprocal of an arithmetic series. So if you have 1, 2, 3, 4, 5, its harmonic series is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. So we want to verify that this is divergent. The harmonic series is divergent. For this particular series, it is convenient to consider the partial sums S sub 2, S sub 4, S sub 8, S sub 16, S sub 32, and show that as they become large, so you can evaluate this by table. So the sum for the first two terms would be 1 plus 1 half. The sum for the first two terms would be 1 plus 1 half plus 1/3 plus 1/4. The sum for the 8 terms would be 1 plus 1 half plus 1 plus 1/3 plus 1 plus 1/4. plus 1 plus 1 over 1 fifth plus 1 over 1 sixth plus 1 over 7 plus 1 over 8, and so on. So, for S sub 2, it would be 1 plus 1 half. For S sub 4, it would be 1 plus 1 half plus 1 fourth plus 3 fourths. We know definitely that 1 third plus 1 fourth would be greater than 1 fourth plus 1 fourth. So, this would be, S sub 4 would be greater than 1 plus 1 half, plus 1 half. So, this would be greater than 1. 1 fourth plus 1 fourth is 1 half, plus 1 half equal to 1. So, it is greater than 1 plus 1. For S sub 8, so this would be 1 plus 1 half. This is 1 half, and this is also 1 half. So 1 plus 1 half plus 1 half plus 1 half. So that would be 1 plus 3 halves. So we know that 4 1 over 8 is smaller than 1 fifth plus 1 sixth plus 1 over 7 plus 1 over 8. Considering as n becomes bigger and bigger, so this becomes 1 half. This would be also being compared to all 1 halves. So we have 1 plus 4 over 2. So as n becomes infinitely large, you would notice that this side would become very, very large. So for s is equal to, for the sum for 32 terms, it would be greater than or equal to 1 plus 5 over 2. For 64 terms, it would be 1 plus 6 over 2. And for the general term for the sum for 2 raised to n, it would be greater than 1 plus n over 2. As n becomes significantly larger, as n approach infinity, so the sum also approaches infinity. So therefore, the harmonic series diverges. So this shows that as n approach infinity, the series becomes approaching infinity as well. So the harmonic series diverges. So for the series, for the test for divergence, if the series summation of a sub n is convergent, then the limit of a sub n as n approach infinity approaches 0. So if the series a sub n is convergent, then the limit of a sub n as n approach infinity becomes 0. So this is an implication and not a biconditional operation. So if the series is convergent, if we have a finite sum, then the last term should be 0, because otherwise we will be having difficulty finding the sum of the series. So if the series summation of a sub n is convergent, then the last term approaches 0. So take note that this is not biconditional, that if a sub n is equal to 0, it is convergent. No. So if a sub n is convergent, then the limit a sub n approaches 0. So the converse of theorem 6 is not true in general. So if a sub n is equal to 0, we cannot conclude that a sub n is convergent. If the limit of a sub n does not exist, or the limit of a sub n as n approach infinity is not equal to 0, then the series summation of a sub n is divergent. The test for divergence follows from Theorem 6 because the series is not divergent. Then it is convergent. So the limit of a sub n is equal to 0. So this is now true that if the limit of a sub n does not exist or not equal to 0, then the series is divergent. So if the last term is not 0, so definitely it would be not convergent. So for some properties of convergent series, if the summation of a sub n and b sub n are convergent series, so the series c times a sub n, where c is constant, so the summation of a sub n plus b sub n and the summation of a sub n minus b sub n, so multiplying a constant is just the same as factoring out that constant. So summation of c times a sub n is equal to c times the summation of a sub n. So for the sum of a sub n plus b sub n, so that would be the sum of a sub n plus the sum of b sub n's. And for the sum of the differences of a sub n and b sub n, it would be equal to the sum of a sub n minus the sum of b sub n's. So let us consider for the proofs, if the sum of a sub I is equal to s sub n, for a sub I equal to, for the sum of a sub i's where I is equal to 1 to n, the sum is equal to the summation of a sub n for n is equal to 1 to infinity, and t sub n is the summation of b sub I for I equal to 1 to n, and t is just equal to the summation of b sub n for n equal to 1 to infinity. So the n partial sum for the series is the summation of a sub n plus b sub n is the sum mu u, summation of a sub I plus b sub I. So for some properties of convergent series, if the summation of a sub n and b sub n is convergent, then the sum of the components would also be convergent. Find the sum of the series summation of 3 over n times n plus 1 plus 1 over 2 raised to n. So the series 1 over 2 raised to n is a geometric series. So this term here would be 1/2 squared, 1/2 cubed, 1/2 to the fourth, and so on. So the first term is 1/2. The common ratio is 1/2. So the sum is a over 1 minus r. So the sum is 1/2 over 1 minus 1/2. So that is basically 1. So as shown here. However, the other term, 1 over n times n plus 1. So we factor out n. So when we factor out n, so it would be a 1 over n times n plus 1. In the previous example, we have 1 over n times n plus 1 equal to 1. So this gives a convergent series. So 3 times 1 plus 1. So that would be equal to 4. So that ends our discussion for today. So thank you for watching.